Welcome. As your skills in physics increase, you may find others coming to ask you for help. If you're under a tight timeline or in a highly competitive environment, you may wonder whether this is a good idea. At the United States Air Force Academy, there's a threefold motto: integrity first, service before self, and excellence in all we do. This question has to do with the second part of the motto, service before self. The United States Air Force, as well as all of our military branches, needs qualified people in order to achieve the mission of protecting and defending our Constitution. Similarly, American businesses, industries, educational institutions all need qualified people. You can contribute to this success by helping your friends succeed in physics. Moreover, when you teach a subject to someone, you engage higher levels of thinking, and by taking different approaches, you deepen your own understanding and long-term memory of the subjects. I'm Dr. Courtney. We're going to use Newton's second law to develop a system of equations describing the motion of this mass spring system, and then we can go on to solve for the specific quantities asked for. Specifically, we will be looking to develop expressions for the position as a function of time, the velocity, and the acceleration as functions of time. Then we can use the given information to find the specified quantities, specifically the angular frequency, the spring constant, and the amplitude of the oscillation. We are not told how this spring mass system is oriented, so I'm going to draw this sketch as if it's oriented horizontally, and we will choose to the right to be we have a spring with a spring constant K and a mass M. We are told that the mass is 60 grams, which is 0.06 kilograms. We are told that the maximum velocity as a function of time is 3.9 meters per second. We're also told that the maximum acceleration as a function of time is 17 meters per second squared. As we make a plan to solve this problem, the first part will be to use Newton's second law to find an expression for the position as a function of time. We will express the acceleration in terms of position, which is actually, if you recall, the second derivative of the position function with respect to time. Then we want to express the force on the left-hand side of Newton's second law in terms of the spring constant and the displacement. Once we set that up, we end up with a differential equation, and we want to solve that differential equation for the position as a function of time. Then we'll be ready to determine the quantities that we're asked for. The way that we'll determine the angular frequency is first to find expressions for the velocity as a function of time and the acceleration as a function of time by taking the first and second derivatives with respect to time of the position function. And then we will equate the maximum values to given values. In this case, we can then solve the system of equations that results. We'll end up with equations with multiple equations and multiple unknowns, And we'll solve this system for the angular frequency, since that is what this part of the question asks for. Then we will be equipped to determine the spring constant K. The way that we'll do that is to return to the statement of Newton's second law and substitute for the displacement x and the acceleration using the expressions we found by solving the differential equation and taking the second derivative with respect to time. Then we'll be ready to solve that equation for the spring constant and compute it. Finally, we are asked to determine the amplitude. To do that, we can go back to one of the expressions that we get when we substitute for the maximum velocity and acceleration in step 2b. And we can substitute values at that point. We may need some simplification. Now we're ready to evaluate this problem. To make sure that we have enough room to work, I'm going to summarize our plan and then be right back. I'm back, and I've summarized our 4-step plan here. As we evaluate the problem, we begin with Newton's second law, which says that the net force is equal to the mass times the acceleration vector. In this case, we're working in the x direction, and so the net force in the x direction equals the mass times the acceleration in the x direction. The acceleration in the x direction can be expressed as the second time derivative of the position function. The force is a restoring force caused by the spring. That's the only force in play here. And it is computed as negative, because it's a restoring force, the spring constant times the displacement. Rearranging this to isolate the differential term, we get minus the spring constant over the mass times the displacement. As we solve this differential equation, we will guess a solution of the form x as a function of t is equal to x naught times the cosine of omega t. Now in this case, when t is 0, x of t is x naught. And if we choose our initial condition to be the release of the mass from the maximum displacement, then x naught, or the initial value, is equal to the amplitude. And so we can rewrite this as the position function equals the amplitude times the cosine of omega t. As we move on to part 2 of this problem, to solve for the angular frequency, we need to take the time derivative of the position function. That is the velocity function, and that is minus omega times the amplitude times the sine of omega t by the chain rule. Similarly, we take the second derivative, which is the acceleration function. You could think of that as the first time derivative of the velocity function, and by the chain rule that equals minus omega squared times the amplitude times the cosine of omega t. Now notice that the maximum value of the sine and cosine function, no matter what the argument is, in our case sine omega t, cosine omega t, is 1. We're given quantities for the maximum values of the velocity and acceleration functions. So the maximum velocity as a function of time symbolically is equal to the maximum value of minus omega times the amplitude times the maximum value of that cosine function, which is 1. Similarly, the maximum value of the acceleration is the absolute value of minus omega squared a times 1. Now the values were given for the maximum velocity are 3.9 meters per second for maximum acceleration, 17 meters per second squared. We can develop two independent equations involving the amplitude and the natural frequency using these two expressions. So solving for the amplitude in each case, we get 3.9 meters per second over omega, and from the acceleration function we get that the amplitude can also be expressed as 17 meters per second squared over omega squared. If we set these two quantities equal to each other, the amplitude is eliminated and the natural frequency is the only unknown. Cross-multiplying and subtracting yields a quadratic equation for the natural frequency. Factoring out one term of the natural frequency, and solving, we get that the natural frequency is either 0, which is not an interesting result for our physical situation, or it's equal to 4.35897, and the units is 1 over seconds, which is the same as hertz. So that's 4.4 hertz to 2 significant digits. I'm going to summarize what we've done so far and be right back for the rest of the problem. I'm back. We've summarized what we've done so far, and we're ready to move on to part 3 of the problem, which is to solve for the spring constant. We do that by remembering Newton's law that the net force in the x direction is equal to the mass times the acceleration in the x direction. And we're going to substitute the spring force, which is minus kx. And for the acceleration, we can express that in terms of the displacement as the second time derivative of the displacement function. We can also substitute for x on the left-hand side so that we have minus the spring constant times the expression for x as a function of time, a cosine omega t. And that is equal to the right-hand side, and we computed that to be minus omega squared a cosine omega t. Now we see that some terms will cancel. The amplitudes will cancel, the negative sign cancels, and the entire cosine term cancels. So now we have k and the mass and omega squared left. So k equals the mass times omega squared, which is a fairly simple calculation. The mass is 0.06 kilograms and the natural frequency as we computed, but we need to use that non-rounded value. And we compute then that k is equal to 1.0584 kilograms over seconds. Now normally the spring constant, if it's given to you in a problem, is in Newton meters. So what's up with this unit here? Let's do a little aside and see if we can make sense of this. 1 Newton is equal to a kilogram times a meter over seconds squared. If we want 1 Newton per meter, we could divide both sides by meters, and on the right-hand side, meters in the numerator and denominator cancel, leaving us with kilograms per second squared. So we see that this unit, squared, right there, is equivalent to a Newton meter. Finally, we are asked to find the amplitude. To do that, we can select either one of the expressions we developed earlier, and I will pick the one that doesn't require me to square the natural frequency. And in this way, we compute that the amplitude is 0.8947 meters. which is 0.89 meters to 2 significant digits. And so now we have answers for each part of the problem. How do we know whether they make sense? First of all, we check our units. And as we go back to our substitutions, omega did come out to be 1/seconds, which is what we expect for a frequency. The spring constant was a little bit trickier, and we needed to do a little more thinking to make sure that those units were equivalent to newtons per meter. And on the amplitude, we have meters per second divided by 1/seconds, leaving us with meters. Since the amplitude is a distance, that's what we would expect. So the units check out. What about the magnitude? What we can do is to use the other equation for A, whichever one you didn't use. That allows you to check both your angular frequency and the amplitude, because your answer should match up with this answer, and if it does not, you have some investigating to do. So from checking the units and alternate way of computing the amplitude, we can develop confidence that our answer is correct.